A bronze wheel turns in the darkness of a shipwreck, counting the hidden cycles of the heavens. A bronze wheel clicks in the gloom of a shipwreck, its teeth meshing with a rhythm that hints at a hidden calendar of the heavens. What device could have been forged 2 millennia ago, capable of tracking eclipses and the cycles of ancient festivals, and then vanished beneath the sea? It is the summer of 1900, and a crew of sponge divers from the tiny island of Antikythera are hauling up a crate of shattered amphorae when their nets snag on something solid and metallic. The divers, accustomed to the salty sting of the Aegean and the weight of stone jars, pull free a corroded lump of bronze, its surface etched with a forest of tiny gears. In that instant, they have lifted a relic that would upend modern assumptions about the technological reach of the ancient world. Beat 1, the accident and the find. The divers were working on the wreck of an ancient merchant vessel that had run aground on the reef surrounding Antikythera. The ship's cargo, a mixed haul of ceramics and metal fittings, was being salvaged by local men under the direction of the local sponge diving community. Among the broken pottery and rusted anchors, the divers uncovered a bronze object roughly the size of a modern wristwatch, its front face broken but its internal teeth still visible where the corrosion had worn away. At first, the find was dismissed as a broken astrolabe or a decorative piece, because no one in the fishing community had ever seen anything like it. The object was handed to the National Archaeological Museum in Athens, where a young archaeologist, Valeos Staris, examined it in a dim back room. Staris, a student of the renowned Panayotis Kavadias, noted the intricate interlocking wheels, each with teeth no larger than a grain of sand, and recorded in his field notes that the piece appeared to be a mechanical device of extraordinary complexity. His observation set the stage for a century-long investigation. Beat 2, the Hellenistic context. To understand why such a device could exist, we must travel back to the Hellenistic world of the 2nd century BC. After the death of Alexander the Great, his empire fractured into a patchwork of kingdoms and city-states, many of which became centers of scientific learning. Alexandria, with its great library, hosted astronomers like Hipparchus, who refined the Metonic cycle, a 19-year period that aligns lunar months with the solar year, and documented the Saros cycle of eclipses. In Pergamon and Rhodes, engineers were experimenting with geared mechanisms for water clocks and automata. The front face of the Antikythera mechanism, as reconstructed from modern imaging, bears dials that display the familiar zodiac, the 19-year Metonic cycle, and the 4-year Olympiad cycle. Beneath these lie smaller wheels that model the 4-year cycle of the Pythian Games and an eclipse prediction system that distinguishes between solar and lunar eclipses. The existence of such a machine implies that Hellenistic scholars possessed not only theoretical astronomical knowledge but also the practical skill to encode that knowledge in bronze gears, a level of analog computation not seen again in Europe for many centuries. Beat 3, modern investigation. The bronze lump remained a mystery until the 1970s, when a team led by Michael Wright of the British Museum applied early X-ray radiography to peer through the encrustation. Their images revealed at least 30 interlocking gears arranged in coaxial trains, each driving the next with a precise ratio. In the 2000s, researchers at the Swiss Federal Institute of Technology Zurich, ETH, used high-resolution X-ray computed tomography to produce a 3-dimensional model of the internal structure. Their scans uncovered a gear train that appears to combine 2 rotational inputs into a single output, a principle that later scholars have likened to a differential. While the term differential is modern, the mechanism does show a way of adding the irregular motion of the moon to a regular solar input, producing a predictable output for eclipse calculations. Each gear ratio corresponds closely to known astronomical periods, the lunar month, the solar year, the Metonic cycle, and the eclipse half Saros, approximately 9 years and 5 months. The team also identified a series of spiral inscriptions on the back plate. When decoded, these appear to be numbers indicating the length of the Saros cycle in days, further confirming the mechanism's role as an analog computer rather than a decorative object. Beat 4, the mystery of its disappearance. Why does a technology of this sophistication vanish for more than a millennium? The Antikythera mechanism is the earliest known example of a geared clockwork device, and while some scholars have pointed to later Chinese devices as comparable, the precise dating of those Chinese inventions remains a matter of scholarly debate. Most agree that the Antikythera mechanism represents a unique moment in the Hellenistic world, where metalworking expertise and astronomical theory converged in a single workshop. Some argue that it emerged from a brief golden age of scientific craftsmanship in Alexandria, where metalworkers, astronomers, and mathematicians collaborated in elite workshops. Others suggest that copies of the device existed but were lost during the Roman conquest, the decline of pagan scholarship, and the rise of a text-based scientific tradition in the early Christian era. Literary sources such as the **** and later Roman engineering treatises mention complex devices, yet no other physical examples have survived. The scarcity of artifacts fuels speculation. Was the technology deliberately suppressed, or did it simply fall out of use as societies changed? The turn, re-examining the evidence ***. Midway through the story, a later re-examination of the fragments recovered in the early 1900s reshapes the narrative. High-resolution imaging of a tiny fragment, previously overlooked, revealed faint traces of Greek lettering on the back plate. Scholars, cautious about overinterpretation, note that the inscription consists of a series of numerals rather than a clear dedicatory text. Some interpret the numbers as a continuation of the Saros cycle count, while others suggest they may represent a cataloging system used by the workshop that produced the device. The fragment does not, however, provide a name of a patron or a definitive dedication. This more modest reading underscores that the mechanism was likely a high-level scientific instrument, possibly produced for a wealthy patron or an academic institution, but the surviving evidence does not allow us to name that individual with certainty. Beat 5, Contemporary Reconstructions ***. The story leaps forward to the present, where interdisciplinary teams continue to peel back the layers of mystery. In 2005, engineers, classicists, and computer scientists at the University of Cambridge built a functional replica using 3D-printed bronze teeth to replace missing gear segments. When wound, the replica displayed the Metonic cycle and indicated solar eclipses for a span of several decades. The researchers reported that the predicted dates matched modern astronomical calculations within a margin of a few days, a notable level of agreement given the fragmentary nature of the original. Yet each reconstruction uncovers new uncertainties. Many gear teeth are irreparably worn, leaving gaps in the mathematical model. Scholars debate whether the device was cast as a single block of bronze or assembled from separate components. More recently, in 2022, a team at the National Archaeological Museum employed laser scanning and machine learning algorithms to propose a plausible arrangement for the missing rear dial. Their provisional model suggests the rear dial may have displayed a series of eclipse prediction indicators, based on the known half-Saros cycle, rather than a full planetary tracking system. While some researchers have speculated about a planetary component, the current consensus is that the surviving evidence does not support a definitive 5-planet display. The focus remains on the device's sophisticated calendrical and eclipse prediction capabilities, which alone place it far ahead of any known contemporary technology. The haunting aftermath ***. The Antikythera mechanism sits today in a glass case, its bronze teeth still turning slowly under museum lighting. Its existence forces us to ask a lingering, unsettling question: if a civilization capable of such precise mechanical computation flourished over 2,000 years ago, what other technologies have been lost beneath the waves, in forgotten libraries, or buried under layers of earth? The mechanism reminds us that history is not a smooth progression but a series of punctuated flashes of brilliance, many of which may have been erased or forgotten. As viewers hear the faint click of the gears, they are left with a paradox. The device is both a testament to the ingenuity of Hellenistic engineers and a symbol of the fragility of technological knowledge. It whispers that human creativity can surface in unexpected places, and that the past may hold more sophisticated tools than our textbooks ever suggest. The bronze gears keep turning, And with each click we are reminded that the line between legend and machine is thinner than we think, inviting endless speculation and debate among scholars and enthusiasts alike.